Hello everyone, welcome to the Material Science class MIG 300. This is chapter 8. In this chapter we are going to discuss the different forms and types of failure of the material, and we're just going to focus over three types of the material failure: the fracture and the fatigue failure, in addition to the creep failure of the material. So let us start with the first type here, which is the fracture, this is the basic of the one of the subjects or the topics which is related to the mechanics of material, known as the fracture mechanics. Fracture mechanics, it means that is to study how the material is going to fail depending on the material ductility or the material properties and material type. So what does it mean, fracture? Fracture, as I said, this is one of the failure of the material. And failure, it means that the material cannot be used, or there is something wrong that it had been happened to this material in the form of fracture, or the form of a fatigue failure, or in the form of the creep. So to understand more what does it mean failure, let us start with the fracture as one of the forms of the material failure. It is the separation of a body or the material into two pieces or more pieces or parts due to an applied stress. Like if you do have a material that is subjected to a force, like during the tensile test, if you recall, while we were discussing the chapter 6, the material was already under tension, and we're gonna keep on stretching the material till it will be separated, till it will be fractured. So this is known as fracture. So the fracture, as I said, it is the separation of the material into two or more pieces due to an applied force or applied stress. So there is a condition here that there should be an applied stress, and the fracture comes because of this applied stress. And the other issue is that this stress, it should be strong enough, it should be big enough to fracture and separate the material into two pieces. And we do have two different patterns or types of the material fracture. We do have either ductile fracture or brittle fracture. So for example, like in this case, this is in case that we do have a perfect, this is a typical example of highly or perfect ductile fracture. This is the pattern for a perfect brittle fracture. In case that the material, it is very ductile material, like many of the metal material, like aluminum, even steel, copper, and so on. If you try to stretch a piece or a wire of copper under the tensile test, if you recall in chapter 6 that the material is going to go through the elasticity or the elastic region, then it's going to proceed through the yield to the plastic behavior. Then at the maximum stress, the material will start to show a neck. Then this neck will start to be elongated further till the material will be completely fractured. So, and this is typical in case that would have a very perfect plastic material, and this material is subjected to a stress, and the type of this stress, it is a tensile stress, as already shown here in the figure. So the material is gonna show a neck, then this neck will be elongated further till it will be completely separated, showing the two pieces after separation will be in this way. So initially this is more like a single piece, and because of this applied stress, the material has been cut into two pieces, and this is gonna be the pattern or the feature of the cutting or the separation of these two separated parts of the material. This, if in case that we do have like they are meeting in a point, like in this case, like they are very sharp at their ends, this indicates a perfect ductile fracture. On the other side, the brittle fracture, that we're gonna have the material in case that it is a piece of glass and you try to stretch it, so it will be perfectly brittle material, and in that case it will exhibit some perfect fracture of the material that you aren't gonna find any sharpness at the end. Instead, the material will be automatically fractured. This indicating that there is no necking. There was no necking that had been appeared, and then the necking should be stretched to fracture. In the brittle case, we don't have this scenario. In the ductile case, we do have the scenario that there should be a necking, then the necking will be elongated till the material will be fractured. But in the brittle fraction, there is no necking, that it should be showing up, and in that case, the material will be completely separated at once without any necking formation. For most of the material, especially if the material still have some ductility, this is like moderately ductile fracture, and this is the common shape of the fractured material, the fracture that of the material in case that the material has some kind of ductility, as I said. So this is the intermediate transition between the perfect ductile fracture and the perfect brittle fracture of the material. Make sense? So how the fraction in the ductile fraction is going to take place, or what are the stages of the ductile fraction? Is it going to be like the brittle fraction that is going to be exist, or is going to be formed without necking, or there should be a necking? Definitely, as we explained, there should be necking formation, and we start by the elongation of the necking till the complete separation of the material. So let us discuss the different stages of the ductile fracture first. So it occurs in ductile material. It is happening in only ductile material where a plastic deformation occurs, or is going to take place before the initiation of cracks. Then we're going to end up with the separation. So these are the multiple stages or the different phases of the ductile fracture. Like we start with necking, as I said, during the tensile test. We stretch the material, it will be neck. So there should be a neck that is going to be formed. Then as we apply it, and this is a condition that we have to keep on increasing the applied stress. That, for example, if the stress is maintained at this level and there is no further increase in the stress, so there is no separation, there is no fraction that is going to take place. The fraction to take place, in case that we do have a ductile fraction, it requires an essential requirement, which is that the applied stress it should be keep on increasing. So if we're going to keep on increasing the applied stress, some voids and cavities, they start to show up inside the material microstructure. So here we are talking about the microscopic scale inside the material. These proceduries or cavities, they are very small in size in the beginning. Then as we keep on increasing the applied stress, these cavities will be kind of merged and start to grow up and start to increase and start to propagate, resulting in forming a crack inside the material microstructure. Probably the crack, it is not necessary to be seen at the microscopic scale. It could be at the microscopic at the microstructure inside the material microstructure. But with time and as we keep on increasing the applied stress, the crack will start to propagate, and this is another phase that we're gonna have a crack propagation till we're gonna end up with final fracture and complete separation of the two pieces or the two parts of the material due to the tensile test. So this is the procedure, this is the stages, these are the features of the different stages of the ductile fracture in case that would have a ductile material. So what are the stages of ductile fracture? We start with large plastic deformation in the material and formation of the necking and crack formation, like in these cases. And then we're going to have crack propagation till we're going to have a complete separation. And so we can represent, we can mention this in the meanwhile, we have to represent the different stages of the ductile fracture. This requires an increase in the applied stress to propagate, as I mentioned, that the applied stress should keep on increasing. For that reason, we're going to say that this crack that is going to be formed here is going to be considered as a stable crack. So what does it mean, a stable crack? The stable crack is the one that is going to keep its shape, maintain its shape, preserve its shape as long as there is no increase in the applied stress. So for example, if we stretch the material up to this stress level and we just form a crack inside the material microstructure, but the material is still here, it is a ductile material. This crack will not be propagated. The crack will not propagate unless we are increasing the applied stress. But if there is no increase in the applied stress, the crack is stable. The crack will maintain its shape and size as it is as long as there is no increase in the stress. Even if we apply the stress, which is lower than this stress level, the crack will not be propagating. So the condition for the crack propagation, for the case of having a ductile fracture or a ductile material, this requires an increase and keep on increasing the applied stress to propagate the crack, and that's why this could be considered the type of this crack as a stable crack. No worries, there is no problem with this crack. Even if the material showed some crack internally inside the material microstructure, there is no worries and we still can use this material. Why? Because the material it didn't show a complete fracture or separation. Why? Because the crack, it is a stable crack, and in order to propagate to the final fracture, this requires an increase in the stress. So we can still use this material at the stress level lower than this stress level. Make sense? The other side here, the brittle fraction. Brittle fraction typically and intuitively it comes from the name, it should gonna take place in a brittle material. So the ductile fracture takes place in the or occurs for ductile material. This one occurs for brittle material, where very small or even no plastic deformation is going to take place before the initiation of the crack. And then we're going to end up with a complete separation of the material. So in the ductile fracture, this is what makes difference between the ductile fracture and the brittle fracture. Ductile fracture that is going to take place in the ductile material, this requires plastic deformation, huge amount of plastic deformation before the crack, before the fracture. But here, we barely could observe any plastic deformation, or barely the material could give any plastic deformation before the formation of the initiation of the crack and the initiation of the fracture process. So you could consider that the initiation of the cracks or formation of the crack inside the material microstructure, it is the initiation of the fracture process, that the material gets ready to be completely separated and fractured. So the stages of the brittle fracture are that we start with crack formation, which is going to form at once with no need to exhibit any plastic deformation. Directly is going to show up. Almost there is no plastic deformation before the crack formation. Then we're going to end up with the crack propagation, which is going to be propagating very quick till the complete separation of the material. So the crack propagation, but for the case of brittle material, the crack is unstable. But in the brittle material, ductile material, it was stable. Stable, it means it requires an increase in the stress to propagate the crack. The crack will not be propagating by itself. It will not be propagating unless we are increasing the applied stress. But here the unstable crack, and this is for the case of brittle material, the cracks would propagate quickly, and it would even continue to propagate without an increase in the applied stress. There is no need even to increase the stress. Even if we're going to keep the stress level as it is, or even at a lower stress level, the crack is going to keep on propagating, and the material, it will be suddenly fractured right away without any plastic deformation. And this is what distinguishes the brittle fracture from the ductile fracture of the material. Make sense? So one of the parts, or basically the study of the fracture mechanics, it is one of the important subjects of engineering in general. And one of the things that we should understand here is how these cracks are propagating. And this is one of the concerns of the fracture mechanics, is to understand the propagation and expect the propagation, how it's going to be. For example, if we have this material, if this crack is going to propagate in this way, or it's going to propagate in a different way. So what is the pattern and the approach by which these cracks are propagating inside the material microstructure? This is the concern of the fracture mechanics. And the other question is why these cracks are propagating because of an applied stress, especially if we're going to talk about the ductile fracture. Case that we have a stable crack, and we said that in order to propagate this crack, there should be an applied stress, and this stress, it should be big enough to keep on increasing and propagating the crack. So to understand how these cracks are propagating, whatever they are going to propagate or not, this requires that we should understand the stress levels around this crack. The existence of the crack inside the material microstructure increases the stress level over what we expecting, even over or higher than the applied stress. So for example, let us assume that you have this plate. In case that this plate is an intact plate, it means that plate without any cracks. So for example, if you have the same plate without any cracks, and this plate is subjected to a stress, and let us name the applied stress as sigma 0. So sigma 0, this is the applied stress, which we could give it a name as nominal applied stress. So if I ask you, think that or assume that you are handling a probe that detects the stress that is going to generate within this plate at any point. Assume that you have this special tool. Assume that you have a probe that you can probe or identify or can determine the value of the stress at any point that belongs to this plate. So if you try to pick or calculate or probe the stress at this point or at any point over this plate, mostly this stress is going to be the same value as sigma 0, which is the applied stress. This is in case that we don't have intact plate without any cracks. or without any crack, whatever it is shown at the macroscopic scale, or even it is at the microstructure of the material. As long as there is no cracks, the stress level will be the same. Uniform stress distribution over this plate. But in case that we do have a crack, unfortunately the stress will be different. If you try to measure, for example, the stress at this point or at this point, any point that is far from the stress, mostly this stress, it will be sigma 0. But as you come close to the crack, so as long as you're far from the crack, the stress, it will be the same nominal applied stress. But as you come close to the crack, whatever this crack, which is an external crack or known as edge crack, this is edge crack that is located at the edge of this plate, or external crack, but this crack, it is an internal crack. This is internal crack. Whatever you do have internal crack or external or edge crack, as long as you come close to this crack, the stress level will start to increase. The stress will be maximum and it's going to keep on increasing. And the stress, it will be maximum at the tips and the edges, at these 2 points of the crack, at this point of the crack. And this is what makes this crack propagates. What makes the crack to propagate and start to crack more and propagate in a certain direction, this is because that the stress around the region of the crack is going to keep on increasing, and it will be maximum at the tippy tip of this crack, at the point of this crack. So how much of increase that we should expect around at the tip of the crack, this could be calculated using this formula, and there are lots of other expressions that depend on the different shapes and different scenarios of the crack itself. And this is, as I said, the concern of the fracture mechanics. Is to one of the subjects of fracture mechanics is to expect or to investigate how these cracks are going to propagate and what is the maximum stress that is going to generate at the tip of this crack. So the maximum stress or the stress that is going to generate at this tip of the crack, it's going to be maximum here. So for example, if we decided, let us assume that we choose a line, this cross section over the plate, and for some reason we decided to track the changes in the stress level as we move from that point coming close to the crack itself. So as you can see in this figure shows you the distribution of the stresses as we come close to the crack. So the crack is here. The crack is here, and this is the edge of the plate, which is this point. At this point, the stress, since we are far from the crack, the stress here is the normal stress, which is sigma 0. Then as we come close to the crack, the stress is going to start to increase, grow up, till it will be maximum at the tip of the crack. Then since it is a crack, so there is no material to calculate or probe. Think, as I said, assume that you are handling a probe. So there is no metal here so you can probe a stress. It is cavity. It is empty thing. So it means that you're going to skip this part. Then you're going to try to probe the crack on the the stress over the other side. You're going to find it maximum almost the same level here. Then it's going to keep on decreasing till it will be minimum again up to sigma 0 one more time over the other side at this point. Make sense? So as you can see, the stress, it will be maximum at these 2 tips, at these 2 points. The same is applied to this crack. So how much is this maximum stress? What is the maximum value of the stress that it could be generated at the crack? And this is the thing, this is the amount of stress needed to initiate the crack, to produce crack propagation within this material in comparison to sigma 0. Sigma maximum is going to be equal to sigma 0, which is the applied nominal stress, times 1 plus A over R rho T to the power half. A stands for this A, it is a characteristic size of the crack. In case that we do have edge crack, and this is very important, the A is going to be the length of the crack. So it's going to be the crack size or the crack length. Or in case that we do have edge crack, in case that we do have internal crack, this A, it should be half the length of the crack. So for example, if it was mentioned that we do have an internal crack of a length of 60 millimeter, so since it is internal, this A should be 30 millimeter. But in case that would have an edge crack, with a length 50 millimeter, so the A is going to be 50. So the A is going to be the length in case of the crack, in case that there is edge crack, and it's going to be half the length of the crack in case it is internal crack. Rho stands for the radius of the curvature of this tip. This tip, basically, it is not a point or a sharp tip, and instead mostly it's going to have like a curvature. So this rho indicates the curvature of this crack at the tip point. And if, as long as this rho it is small, as we are decreasing the value of this radius, this is going to increase the amount of stresses that is going to generate here, because the power here it is half. It is not, it is a fraction, so the increase in the denominator is going to increase the amount of the stresses that it should be generated at the tip, and this indicates that there is a high possibility of the crack propagation. So this is known as, from this sigma m, if we divided the ratio, or we calculate the ratio between the maximum stress that is going to generate at the crack tip over sigma 0, this gives a factor known as the stress concentration factor. And we are using this factor in our design application as engineer, especially mechanical engineer. We should have an idea about this stress concentration factor. What is the ratio between the maximum stress that is going to generate at this step to the sigma 0, which is the applied stress? So in order to keep this material without any further crack propagation, we have to keep the stress level lower than this sigma 0, so we could avoid the crack propagation. Make sense? And this what introduces the stress concentration. The stress concentration, and this is another thing. What makes, the question is, what makes the stress at this tip of the crack increases? We were discussing so far that the stress is going to keep on increasing as we approach or come close to the crack. Why? This is because of a phenomenon known as the stress concentration. Stress concentration of the material has an internal crack or even surface crack or edge crack. As I mentioned, the applied stress will increase to reach its maximum value at the crack tip. The maximum stress, as we mentioned, it can be calculated using this expression, and if you divided the maximum stress over sigma 0, this gives the stress concentration factor. So this is a factor that indicates how the concentration, or gives an idea about the concentration of the stresses. So still the question is, what is the stress concentration? To understand the stress concentration, let us try to draw some patterns or lines that indicate the flow of the stresses or the amount of the stresses through the material. So in case that would have intact plate, there is no internal cracks. So the stress, it should be like the stress levels, it will be, or lines, it will be represented like parallel lines. All of them are parallel. But for example, in this case, the stress here, it will be like a straight, then it, as long as it comes close to the crack itself, to the edge crack, it's gonna try to skip the crack and it's gonna move to the other side. So this line here is known as the stress contour line. Think like this is a particle and it would like to move. Assume that this is one point or one particle, and you just gonna track or trace the path of this particle through the material to the other side. So as long as it moves, comes close to this crack, it's gonna skip the crack and the cavity because it won't gonna able to move through a cavity or an empty space. And then you're gonna have another line or another particle, another contour line, so it's gonna be swerved somehow in that way, and carry on. So if you just gonna keep on going till you're gonna have like kind of a straight line, as you can see here, it is kind of a straight line. Then there is another crack, right? So if you're gonna come close to this crack, so it will be curved somehow, and then you're gonna continue. Then at this one, you just gonna skip the crack. Over the other side, for example, it's gonna keep over. So you're gonna end up with kind of similarity in that case. So all of this line known as the stress contour lines. All right, so till it will be like kind of straight. So as you can see, if we decided to track these contours, so you're gonna find in this case, let us choose or work over the crack in the middle. the internal crack. So you're gonna find around this area, these contour lines are very crowded, like it becomes very crowded, and the spacing between these lines, it comes very small, as long as, especially as long as we come close to the tip itself. This indicates that the stress, it will be very crowded here and it will be more concentrated at the tip. And that's why this what does it mean is stress concentration. It means that, think of it like particles or points are moving. So as these points are coming close to the crack itself, these particles or the spacing between them or the spacing between these contour lines of the stress will become very, very close. And this what increases the stresses, due to something that we call the stress concentration phenomenon. And this is what makes the stress at the crack tip increases. Make sense? So this is some of the things that we are studying or considering as long as we are working over the fracture mechanics of this material. And this is one of the important subjects of the engineering. So to measure the material's ability to withstand the fracture due to the crack propagation or this fracture behavior of the material, this could be measured by a factor which is known as the fracture toughness factor. This fracture toughness factor, which is KIC, is a measure of the material's resistance to brittle fracture. So it is to brittle fracture in the presence of the crack. So why we mention the material ability to resist the brittle fracture? Why brittle fracture, not ductile fracture? Because the problem is with the brittle fracture. Why? Brittle fracture here indicates that you're gonna have unstable crack. We said that the brittle fracture, it is distinguished with unstable cracks, and these cracks are automatically, or they're gonna continue to propagate even with no need to increase the applied stress level. So the issue is with the brittle fracture. But this doesn't mean that in case that we have a ductile material with stable cracks, this material doesn't have a fracture toughness. No, it do have a fracture toughness, but it is very high. So the fracture toughness, it is a measure of the material's ability to avoid the crack propagation without increase in the applied stress. You could understand it in this way. So in case that the material, it's a crack, could propagate without an increase in the stress, so we are expecting that this fracture toughness is too small. It is very low value. But on the other side, in case that the material, it is ductile material and most likely to have stable cracks and to have ductile fracture, this material will have a fracture toughness that is mostly going to be very high fracture toughness value. So it is a measure of the material resistance to brittle fracture in the presence of cracks to avoid the crack propagation. And generally speaking, in case that we do have a material with a crack, this crack could propagate depending on a factor that is known as the stress intensity factor. So it is, don't be confused with the stress concentration factor and the stress intensity factor. The stress concentration factor, it gives an idea how about the maximum stress that is going to be generated at the crack tip. And whatever, in case that this maximum stress, it is bigger than a specific value that is needed to propagate the crack will start to propagate. But in case that this maximum stress, it is lower than a certain value of the crack propagation, this crack will not be propagating. Make sense? But here, the stress intensity factor, also it is another factor that most likely related to the fracture toughness. Also somehow it should be related to the stress concentration factor. But anyway, this Ki, just distinguish between Ki, which is the fracture toughness, that it should be different than KIC, which is a material property. So this KIC, it depends mostly on the material type, but this Ki, it is a factor that we calculate depending on the geometry with no regard to the material type. It depends on the applied stress and the geometry of this plate. Like for example, in case that you have a plate with an internal crack or a plate that is with an edge crack, and these two plates are subjected to two tensile forces in this way, so the expression for this is stress intensity factor just for the case of plane strain, it will have this expression, but for any other cases it would have a different expression. Here the interest is just to give you an idea about this stress intensity factor, but as I said, the concern of fracture mechanics is just to study these different stress intensity factor for different cases, for three-dimensional problem, plane strain, plane stress problem. So this is a very general subject, but here just for the case of plane strain, it's gonna be calculated as y times sigma 0 square root of pi a. Why? This is an undimensional parameter that depends on the material geometry and the shape of the crack and the crack dimensions. For example, for the case that we do have a plate that is subjected to a tensile force, and this plate has an internal crack, and the other condition is that the distance between the crack and the four edges of the plate are very far, are very big distance. So in that case, this y is going to be 1. But in case that we do have the same plate that is also subjected to tensile force, but the distance between, and this crack, it is an edgy crack. Edgy crack, it means that it should be located over one of the edges of the four. But in the meanwhile, the distance between this crack and the other three edges, it is very far distance. So this y is going to be 1.1. For any changes over the geometry or the crack, y is going to take different values. So y is not a specific value. As I said, it depends on the applied stress. It depends on the geometry of the plate. It depends on the crack size and where it is located inside this material, right? So there are lots of features that would identify, based on which we could identify why. One of the things, for example, in the mechanical design for the mechanical engineers, there are lots of tables from which you can identify this value of y, and then you're gonna plug it here. Sigma 0, this is the applied stress, which it should be in that case a tensile stress to allow for the crack propagation. These cracks, they will not be propagating unless we are applying a tensile stress over the material. But under compression stresses, there is no possibility for the crack to propagate, mostly in the conventional case, and in that case, this Ki will be 0. You should consider it 0. So in case that sigma 0 is compressive stress, Ki, the stress intensity factor will be 0 in that case. But in case that it is positive tension stress, it's going to take a value depending on this expression. A stands as the crack size, the maximum. This is the sigma 0, the maximum applied stress, the A, which is the crack length. As we discussed over the previous slide, this A, it could be half the internal crack length, or it could be the same crack length in case that we have an edgy crack. So depending whatever you have an edgy crack, so you're gonna take the whole crack length, plug it here. Case that you have internal crack, take half of it and plug it here. You're gonna end up with the stress intensity factor. In case that the stress intensity factor, as you can see, this intensity factor depends on the applied stress, depends on the geometry of the material, depends on the crack size. If this stress for this problem, for this case, depends on the this case was bigger than the fracture toughness, which is a material property, in case that it is bigger than the fracture toughness, this crack is expected to propagate. But in case that this intensity factor, it is lower than the fracture toughness of this material, so no worries about this crack, and we can keep on using this material with no worries, because we are not expecting a crack propagation. Make sense? So this table, for example, gives different values for some examples of metals, ceramics, and polymers, and their equivalent fracture toughness factors, how much it is. For example, if we're gonna observe these metals, so all of these materials, these are metals. As you can see, their fracture toughness, it is kind of good value. It is 24 megapascal times square root of m. This is the unit, the basic unit for, or the unit for the fracture toughness. For example, the aluminum alloy, it could be around 24, 44, depending on the alloy type. Titanium, for example, it's gonna be bigger. It is more tough than aluminum. Steel, it is more tough than aluminum, definitely, and even it could be more tough than the titanium alloy itself, right? But as you can see, somehow in the metal material, the toughness, it is not necessary to be related to the material yield strength. The material yield strength, as we discussed in chapter 7 and 6, This is a measure of how strong this material. We probably do have a material with a high yield strength and it has lower toughness. Like for example, this type of aluminum alloy, the yield strength here is 495 megapascal, and the toughness factor, the fracture toughness, it is 24. Here, this material has a lower yield strength but higher toughness. So the toughness, it do depend on the material type, and it depends mainly on it is related somehow to the material ductility. How easy the dislocations and the grains would move inside the material, as we discussed inside the material microstructure. This is more likely related to the ductility, and this definitely affects the fracture toughness. But for example, if we're gonna proceed to the ceramic materials, even polymers, and we compare their fracture toughness to the ones of metals, as you can see, both are very low. Like the fracture toughness of these ceramic materials is very low, especially glass. Glass, for example, it is 0.7 up to 0.8. Very small value. Concrete, it is very low toughness. It cannot support tensile forces. Remember that this toughness to allow for crack propagation requires tension. The ability of the concrete to support compressive forces, it is very high, but it is very weak when it is subjected to tensile force. The same thing for the glass. It could support some compressive forces, but it is very weak under tension, so it will be completely fractured. But anyway, its toughness, fracture toughness for this ceramic material, it is very low. The reason is that because they are brittle. The reason for ceramic material of the low fracture toughness of ceramic material, because they are brittle. But polymers, in the meanwhile, they are ductile material. Many of polymers are rubber material, for example. They are ductile material. So why we still have low fracture toughness for polymers? The reason that they are weak. So why the fracture toughness in polymers, it is low than metals? The reason that polymers are weak materials in comparison to the metal material. As you can see, their yield strength, it is very small in comparison to the strength of the metal material. So that's why this is a reason why they have, despite they are ductile materials, they do have low fracture toughness because they are weak. But ceramics, they are strong, but in the meanwhile, they do have fracture toughness, which is low because they are by nature, they are brittle, and this makes their cracks are that micro cracks when it is or appears inside the material microstructure, they are unstable, and definitely the material is going to fracture automatically. Make sense? Fatigue is another mechanism of the material failure. Fatigue is different than fracture. Fracture, we said that the material, it should be subject to a very high stress that is big enough to allow for the crack propagation, and then as long as this applied stress it is there, this material, this crack will propagate very quick and the material will be directly fractured. But the fatigue is another. So the fracture, it is an indication of a material failure, but it is a mechanism that is different than the fatigue. Fatigue is another mechanism of the material failure. It is a form of a material failure that occurs in materials subjected to dynamic and fluctuating stresses known as the cyclic stress. So in case that the material is subjected to a dynamic stress, so what does it mean this? To explain it to you, let us assume that you do have a shaft or a beam like this one, and somehow it is fixed from this side, supported from this side, and it is here supported from the other side by some tools and methods, and there is a force that is already applied over this beam or shaft. So as long as this beam, it is stationary, not moving, not rotating, there is no any kind of motion that it would be used or generated for this beam, and in the meanwhile, in case that the force, it is constant in terms of magnitude and direction. As you know from physics, force, it is a vector quantity. To be fully described requires a magnitude value as a value and a certain direction. So in case that the value and the direction both are constant, they are not changing for the force. In the meanwhile, this beam is not moving This kind of problem is known as a static problem, static. So under the static condition, there is no fatigue. So again, in case that you have this beam not moving, the force is not changing direction or magnitude, this type of the problem will be considered as a static load problem or a static problem, and in that case, there is no fatigue effect. There is no possibility for this beam to fracture by fatigue. It could fracture or it could fail because of the fraction, not because of the fatigue. Why? Because there is no dynamic load. The fatigue requires a dynamic load. So the question is how the dynamic load could be generated. The dynamic load, any other thing than the static case, it will be counted as dynamic. For example, one of the things you probably do have, this beam is fixed, stationary, not moving, not rotating. But the force, it changes direction. Just the direction of the force. Like the force, it is constant as a value. The beam is not moving, but for some reason, the direction of the force is going to keep on flapping or switching. So it's going to keep on push, then it's going to push up, push down, push up. And it's going to keep on repeating this for a long time. This is known as a cyclic stress. So it is like one cycle push down and up. This is one cycle. Down and up, a second cycle. And keep on repeating. So this is known as a cyclic stress. So there is a possibility, there is a high possibility of this material to fail, and the failure in this case, it will be because of a fatigue effect. Another scenario of the fatigue, which is relevant to the dynamic load, in case that the magnitude, probably the force direction could be the same. The force direction is the same, the beam is stationary, not rotating, not moving, but the magnitude, the value of the force is changing. In that case, it means that, for example, you're going to keep on pushing with 100 Newton, then 200, then 100, 200, 100, 200. So it is a cyclic load. Still, it is a dynamic, and there is still a possibility of a failure of the material because of the fatigue. This is another form of the fatigue failure. Not form, but this is another scenario or option of the fatigue failure because it's still of a dynamic load, that the force changes magnitude only. Even if the force is not changing magnitude, it's not a changing direction, that the force is constant in terms of magnitude and direction, but the beam is rotating. So in that case, it becomes like a shaft, something that rotates about these two bearings. Think that these are two bearings that gives free rotation around the axis of this shaft. So as long as this shaft is going to keep on rotating, we still have a fatigue. How? The force is constant in terms of magnitude, it is constant in terms of direction. Why we say so? There is no switching in the direction. Why we still have a fatigue? To explain it to you, just to let you know, let us give 2 marks here. Let us mark, this is the blue side of the shaft, and this is the green side of the shaft. So assume that you have taken a picture of the shaft at this position. Remember that the shaft is going to keep on rotating, and just take one picture. So the picture, when we took the picture, we find that we just put 2 marks over the shaft, and we find the blue mark is on the top. In that case, and remember, the force is not a changing magnitude or direction. So, and because of this force, this shaft should be bended down. So the bending, if we try to observe the curvature or the bending of the shaft, you're going to find that the blue side of the shaft will be under compression, while the green side of the shaft will be under tension. The blue side will be under compression, the top surface, because the blue is located over the blue mark over the top surface, which will be under compression, while the green mark now it is under the bottom surface and it will be under tension. So there is a difference here in the stresses. How about if you're going to leave this, allow for the further rotation, and you're going to take another shot or picture of this shaft, and for the new picture, for some reason you found that the green mark became on the top, while the blue mark, it was located over the bottom surface. Then you're just going to apply. So you are not marking anymore. You just put from the beginning 2 marks, then you rotate the shaft and take a picture. So we found that the mark in the beginning was on the top, the green, the blue mark was on the top, the green was on the bottom. Then we rotated again and we took another picture, and this time we found that the green marker is on the top and the blue marker is on the bottom. And the force is still the same, force in terms of magnitude and direction. So in that case, the side, the green side, it will be under compression. Remember that the green side in the first picture, it was under tension. Now it became under compression. The blue side was under compression, now it became under tension. So this is a change in the stress, but it is indirect. It is indirect change of the force. It is direct change of the stress that comes because of the rotation of the shaft. So as long as this shaft or this object, the solid part or the material is moving, or the force changes magnitude or direction, there should be a possibility for that this material to fail, or in case that this material is failed, this probably because of a fatigue effect. The fatigue effect is going to be a big deal and is going to come into play, and it should be considered in that case. Fatigue failure is usually associated with brittle fracture. Brittle fracture, as we said, that this is conjugate to the crack propagation, because there are some, it is very similar to the same idea of the brittle fracture, and it is little in ductile material. It is little, this is not necessary actually, but to be more accurate about these two statements, that in case that we do have ductile metal, mostly it could survive longer than the ceramic material in terms of fatigue. So that's why, for example, metals are used a lot in so many machines and engineering application, because of their ability to support and their ability to, they are tough material in terms of the fracture, to avoid the failure due to fracture, or even they do have ability to avoid the failure of the material due to fatigue. So what does it mean, a cyclic stress? It is the stress that it changes its magnitude and or direction with time. As we said, we should have a change in the stress in terms of magnitude and direction, or both, with the time over a cycle. It's going to repeat itself. The applied stress may fluctuate with 3 different modes, and there are more actually, but these are the 3 different modes that mentioned in the textbook. One is the reversed stress, repeated stress, and random stress. Reversed stress, in which the applied stress has maximum and minimum limits of the same amplitude, but the repeated stress has maximum and minimum limits of different amplitude. To understand the difference between reversed and repeated, in the repeated, the material will have, this is the 0, this is the datum, this is the reference. So we start from this value, for example, and then the stress is going to keep on increasing till it will be maximum. This is the stress that applies over the material. And then this stress is going to keep on decreasing till it will be minimum here. Then it's going to keep on increasing again to be maximum, and it's going to repeat this cycle. So this is one cycle of the load. Make sense? If you're going to compare the maximum value of the stress to the minimum value of the stress, they are different values. Like the distance here is different than there. For example, this is a typical example of this, that you are applying a force, and the force is going to change its value and direction. For example, like you apply a force going down with 100 Newton. Then you're going to push it up. You're going to switch the direction to be the upward force, but with 50. So the maximum value is different than the minimum value in terms of value. In terms of the maximum stress is different than the minimum stress in terms of the value. We don't care here about the direction as much as we care about the value and the direction. Actually, we should consider both. But anyway, the value itself, focus over the value just to make it easy for you. We do have one direction with 100 Newton and the other one with 50. So the maximum and the minimum limits of the stress are different. This indicates a repeated stress. But the stress, it could be reversed in case that the maximum and the minimum, they do have the same value, but two opposite directions. So the direction here, it should be considered to be reversed. Like you're going to apply 50 going down, 50 going up. So the 50 up or down, they are the same value, 50 and 50. So this indicates a reversed stress. Random stress is in which the applied stress is very random, that randomly changes over time, like in this case. And this is the common thing that would be exist. But in many of the cases, we are assuming some of these things in order to do the calculation or the design to avoid the fatigue failure of the material when it is used or implemented in a certain application. Make sense? So how we can measure the material's ability, like what we have done in the fracture mechanics or the fracture behavior failure of the material, how we can measure the material ability to avoid the failure due to fatigue. This requires something that we test the material through a fatigue test to extract something that we call as SN curve. S stands for stress, N stands for number of cycles. So to understand more the fatigue, and why it is related to the cyclic load. If we're going to consider, assume that you already handle it to make it easy for you. Assume that you have a wire, a piece of wire using your hands, and I'm going to ask you to keep on bending this wire up and down. So you're going to bend it down, then you're just going to bend it up, and bend down and bend up. But keep on bending the wire up and down till after a certain number of cycles. So if you just bend it down and up, this is one cycle, another down and up, another cycle, down and up, another cycle. If you're going to repeat these cycles after 10 or 20 or 100 or 1000 number of cycles, this wire will be broken, will be separated into two pieces, indicating a failure in the wire. Why the wire didn't fail from the beginning? Because the applied stress, the bending that you do, was not big enough to break this wire or to cut it twice. But after the second cycle, it is surviving, no problem. Third cycle, after 100 cycles, there is nothing wrong with this wire. But for example, after 200 cycles, there are some micro cracks that is going to start to show up inside the material microstructure of this wire. So what's going to happen, as long as you're going to repeat more cycles, these cracks will start to propagate. After certain number of cycles, these cracks will be merged together and will result in a complete fracture in the material and separation of the material. So these are the stages of the fatigue failure. It is not after one cycle or even 1000 cycle or even 10,000 cycle. It depends on the material type and the geometry and the type of the stress. So how we can measure the ability of a certain material to withstand the fatigue failure or to avoid the fatigue failure? This requires the fatigue testing. If a material is subjected to a cyclic stress, it would fracture after a certain number of cycles. It won't gonna fracture from the beginning. If it's going to fracture from the beginning, this is fracture failure, not a fatigue failure. Fatigue failure requires cyclic load, and after a certain number of cycles, it's going to fail. Of this cyclic load stress, the material is going to fail. To determine the number of cycles at which the material would fracture or fail due to the applied cyclic stress, a fatigue test is carried out to extract the SN curve. The SN curve, as I mentioned, it stands for the stress, N stands for the number of cycles till the fracture. So in this test, a series of tests are performed or carried out by subjecting a material or a specimen of that material to the stress cycling at a relatively maximum stress amplitude, and the number of cycles to failure is counted. Data are plotted as stress versus the logarithm of the number of cycles, which is to failure, which is N. This gives the SN curve. So just to give you a hint about this SN curve, how it is done, or this experiment. Think like, for example, you do have a bar. This is one of the things that is fixed, and it is subjected to two forces, into one force at the tip. But this force switch direction, and we're gonna apply a force that is equal, for example, like a force. In the beginning, we're gonna apply a force, let's say like 10 Newton and negative 10 Newton. So it's gonna be tension with 10, compression with 10. So this is one cycle. So 10, negative 10, one cycle, 10, negative 10, two cycles, and so on. and there is something that is going to count the number of cycles. So we're going to keep on stretch and compress this bar certain number of cycle at this load value, and we're going to count how many cycles, and we're going to keep on observing and counting the number of cycles till this bar it will broken, it will be separated. So let's say that we got the number of cycles, let's say like around 10 to the power 6, 1 million cycles. So that's why it is a very long test, takes very long time to finish this test. Then you're gonna prepare another sample of the same material, the same size, very typical to this bar, but this time we are going to increase the force. We're gonna make it like 20 tension, 20 compression, 20 tension, 20 compression. Repeat the cycle, count the cycle. After, for the 20, we got the number of cycles, let's say 10 to the power 5. It should be less, it should be lower. Why? Because we are applying more force, so we are expecting the failure earlier. We are expecting the material will fail at a lower number of cycles as we increase the applied stress. So then we're gonna repeat the process again, and in this case we're gonna consider this force at 30. We got it the after 10 to the power 4. This is the number of cycle till failure. Then 50 and so on till we reach, or we're gonna repeat these forces and keep on increasing the force till we a certain value, which is like around 10 to the power 3. Then we're gonna stop the test mostly. Then we're gonna record this data over a figure, which gonna be this figure known as the SN curve. So over this vertical axis, we putting the stress amplitude, and I'm gonna let you know what does it mean stress amplitude. It is relevant to the applied stress, to the 20, negative 20, 20, negative 20, or 30, negative 30. So this is the amount of stress, and this is the corresponding value of number of cycles till failure, which is N. So that's why we got the name as SN curve. But as you can see, these are these SN curves for two different materials. One material like this one, as you can see, the curve is gonna keep on going down, then it will have like a constant value. But this one is gonna continuously decreasing, declining, and so on. So what is the difference? In case that we have this straight horizontal line, this indicates a material with a fatigue limit, but this is in case that we have a material without a fatigue limit. So what does it mean? This, depending on the material type, the material could have a fatigue limit, and I'm gonna let you know what does it mean fatigue limit, or the material could have no fatigue limit. So what does it mean fatigue limit? Fatigue limit known also as endurance limit. This is the stress below which the fatigue failure will not occur. Theoretically, in case that the material is loaded, in case that you have a material with a fatigue failure, theoretically this material is not expected to fail, and it is expected that this material can live forever as long as the stress that you are applying over this material lower than the fatigue limit. For example, if you subject the material into stress higher than the fatigue limit at this stress level, for example, so the material is expected to fail. If you move horizontal and cut with the curve and move down, we are expecting that this material will fail after this number of cycles, like around 9 times 10 to the power 4 number of cycles, the material is going to fail. If you are going to increase the stress further, the material will fail faster, that the number of cycles will be lower. If you are decreasing the stress that you are applying over the material, the number of cycles is going to increase. But how about if you are applying a stress that is lower than the fatigue limit? For a material with a fatigue limit, theoretically this material will live forever. There is no curve to intersect with. It means that this material, there is no worries of the fatigue failure, and in that case, if the material is going to fail, mostly it's going to be because of other thing, not the fatigue failure. Make sense? But in case that the material is without a fatigue limit, so it means that this material will fail after a specific number of cycles, no matter what is the applied stress, whatever it is, high or big. Even, for example, for a very low stress level, you're gonna find an intersection with the curve and it's going to fail. In terms of engineering application, just to let you know, in terms of engineering application, and this is what we do in terms of mechanical design, in case that the material can survive 10 more than or equal 10 to the power 6 number of cycles, this indicates that for us it is a very good number of cycle, and this material for us, it is like it's gonna live forever, theoretically. So 10 to the power 6 or higher, it is a very good number of cycle, and we can use this material for this application with no worries. Make sense? So this is the basic idea of the fatigue test. From this fatigue test or the SN curve, we can determine the fatigue limit or the endurance limit of this material. For example, what is the endurance limit for this material? Is going to be this value. Just seek the value next to this line. This is going to be the fatigue limit. But what is the fatigue limit of this material? This material has no fatigue limit. What is the fatigue strength? The fatigue limit and the fatigue strength, these are stresses. But the fatigue life, it is number of cycle. So the fatigue strength or the fatigue limit, they are measured by the stresses that needed to achieve a certain number of cycles. Like for example, the fatigue strength of the material, it is the stress level at which the failure will occur after a specific number of cycles of the fatigue or the cyclic stress. For example, what is the fatigue limit? What is the fatigue limit? What is the fatigue strength of the material for 10 to the power 5? It means that the 10 to the power 5, the number of cycles should be the input, and you're gonna seek a value for the stress. So in case for the 10 to the power 5, your objective is just to go up, starting from the 10 to the power 5 and intersect with the curve. Go horizontal to the left. Find the value of the stress. This is going to give you the strength, the fatigue strength of this material at this number of cycles. So the fatigue strength is the amount of the stress level that is needed to, or at which the failure will occur after this specific number of cycles. It means that the number of cycles should be given, then you are seeking a stress. But the opposite for the fatigue life. Fatigue life, the number of cycles. It is the number of cycles that is required to cause fatigue failure of the material when it is subjected to a specific stress level. It means that the stress level will be given and you are seeking the number of cycles that is needed to fail the material. This is known as the fatigue life of this material. Make sense? Another thing that to understand about the crack propagation, as I said, that or the phase or the stages of the fatigue failure, as I explained very quick, we said that we start by crack initiation. In the beginning, after 1 cycle, 2 cycles, 3 cycles, there is no cracks. Then after a specific number of cycles, cracks will start to show up inside the material microstructure. So this is the first stage, which is a crack propagation, and this requires a specific number of cycles. It is not necessary that the cracks generate after the first cycle. No, it mostly is going to take a specific number of cycles known as NI. I stands for initiation of the crack. After a certain number of cycles, the applied stress, cracks would form and start to show up at the high stress concentration regions, and will start to show up inside the material microstructure. Then the cracks will start to propagate. As we are applying more cycles over the material, the cracks will increase with the cycles of the applied stress. So there is another number of cycles that is needed to keep on propagating the crack till the crack will be merged together, till the complete final failure of the material, the complete separation of the material. So if we decided to calculate the total fatigue life, we said that the fatigue life is the number of cycles needed to fail the material for a given stress level. So at this stress level, what is the fatigue life? It is equal. We can get it directly from the SN curve, or even we can calculate it depending on the number of the cycles needed to initiate the crack, which is NI, plus the number of cycles needed to keep on propagating the crack till the final failure. So NI, this is the number of cycles for crack initiation, and NB is the number of cycles for the crack propagation to failure. Make sense? These expressions are very important to use, and this is what we basically use when we are investigating or studying the fatigue behavior of the material or the fatigue stress that would be generated over the material. One of these type of stress is known as the mean stress. As I said, during the fatigue test, or because of the dynamic force, the stress is going to change from maximum to minimum. So which one of these stress? So as you can see, the stresses are not fixed. There is no specific stress value. So basically, in terms of engineering application and mechanics of material and even fatigue, we should know a specific value of the stress to use in order to calculate and expect how long this material would survive under this applied stress. But which stress? Especially in the SN curve. In the SN curve, we are applying different stresses. In the one test, we are applying sigma maximum and sigma minimum. And something also that you should understand, that the stress is not changing from maximum to minimum suddenly. No, the stress increases from 0 to be maximum, then it's going to decline again. It means that there are lots of stresses. Which one it will be represented over the SN curve? Over the vertical axis, we can put here either the stress amplitude, which is this one. This stress amplitude is going to be the maximum negative the minimum over 2. This is what we basically do or conventionally do when we do the fatigue test to extract the SN curve. The stress, which is said that it will be represented over the vertical axis, it will be the stress amplitude, which is the maximum stress negative the minimum stress over 2. As I said, the stress changes between maximum and minimum. And it takes different values, so many different values, which value that we should use for the SN curve, the stress amplitude. But also, we could use range of the stress, which is the maximum negative the minimum. We could use the mean stress as maximum plus minimum over 2. But mostly, as I said, we are using the stress amplitude. Also, there is a stress ratio. There are some of the phenomena and properties of the fatigue failure of the material that would depend on the stress ratio as sigma minimum over maximum, or the mean stress, or the range of stress, or the stress amplitude. One of the things, for example, is the fatigue failure criteria or criterion. And we're going to consider only one criterion here, which is the Soderberg fatigue criterion. This criteria, fatigue criteria in general, there are a lot. One of them is Soderberg fatigue criterion. So this is just one of them, but there are some other types of fatigue criterion, but we weren't going to consider. We're just going to focus over the Soderberg just to give you an idea what does it mean, a fatigue failure criteria. The fatigue failure criteria, they are measures or criteria. For example, it is a measure or an indicator. Whatever we gonna have a failure of this material because of the fatigue or because of any other thing. For example, if you do have a material that already failed and you would like to measure or to investigate what is the reason behind this fatigue, is it fatigue? This failure, it is fracture or fatigue failure. There is a measure, there is an indicator, there is a criterion based on which we can judge whatever we do have a fatigue failure or not. So according to Soderberg fatigue criterion, this is the expression that you are just going to calculate this sigma equivalent. The sigma equivalent, it is the equivalent amplitude stress or stress amplitude. The stress amplitude, which is this value, sigma maximum negative minimum over 2. So this is the applied. This is the sigma A, this is the applied stress amplitude that comes from the stresses maximum and minimum that already acting over the material. But this sigma equivalent, this is the equivalent stress amplitude that the material can withstand. So you're going to deal with this sigma equivalent. This is the maximum stress. Or in other words, this is the maximum stress amplitude. This is the maximum stress amplitude. This is the highest value of the stress amplitude that the material can withstand without fatigue failure. In case that the applied stress amplitude, that because you're going to have the material is going to be subjected to sigma maximum and minimum, in case that sigma maximum negative minimum over 2 is bigger then this equivalent, this maximum or limit of the stress amplitude, there is a fatigue failure that is going to take place. So again, we, according to Soderberg fatigue criterion, that we calculate the sigma equivalent using this expression, and we're going to discuss these different definitions here. Does it mean sigma fat and sigma m, sigma y? So once we calculate this sigma equivalent, and you are subjecting the material into a stress amplitude based on this sigma maximum and minimum, in case that this stress amplitude, the applied stress amplitude, it is bigger than the limit stress amplitude, there is a fatigue failure that is going to take place. But if it is lower, there is no fatigue failure. Make sense? So what is this sigma FAT? Stands for fatigue limit. So sigma FAT is the fatigue limit or the endurance limit of the material. As we discussed, we may have a material with an endurance limit, and mostly, like steel, for example, it has an endurance limit. So that's why steel is mainly used for making shafts and gears, because these machines, these components are used in machines and they are moving. So all the time, by definition, they are subjecting to fatigue failure. So that's why we are using steel, because it has a fatigue limit. So it is a very good material to use for this application to support the fatigue failure. So this sigma FAT, this is the fatigue limit or the endurance limit of the material that you can extract from the SN curve, or you can determine by experiment, or it would be given to you. And you plug it here. Sigma M, this is the mean stress, which can be calculated as the sum of the sigma maximum plus minimum over 2. And sigma yield, this is the yield strength of the material that we measured by the tensile test, as we have done in chapter 6. So this is the yield strength of the material. If you plug this data here and you calculated the equivalent, this sigma equivalent, this is your reference. In case that the stress amplitude that is applied over the material, it is lower than the sigma equivalent, so there is no fatigue failure. But in case that it is bigger, there will be a fatigue failure in the material. Make sense? So to explain this further, let us consider this example of a cylindrical 1045 steel bar. This figure here gives the SN curve for different materials. And something that you should carefully observe is what is written here over this vertical axis. It is stress amplitude, or stress mean, or stress, or whatever. It is, as I mentioned, conventionally in many of the cases, the conventional form of the SN curve that we are reporting the stress amplitude over the vertical axis versus the number of cycles till failure. This is N. Make sense? So these are three curves of the SN curve for three different materials. As you can see, steel, it has an endurance limit or has a fatigue limit, but aluminum or brass, they don't. So that's why if we're going to think about making gear shafts that used in machines, we are depending more on steel. We cannot do, for example, the gears or shafts or these mechanical elements that used in machines from aluminum or brass. Why? For so many reasons. One of the things, these materials are very weak material. In addition, they don't have endurance limit in terms of mechanical applications. But anyway, this material, assume that you have a cylindrical 1045 steel. This is one of these types of the steel. We have so many types of different types and forms of the steel. This is one of them. We do have a steel bar which is cylindrical, and this is the SN curve for the steel, is subjected to repeated compression, tension, stress. So what does it mean? It means that you do have a bar like this one. This bar is made of this material 1045 steel, and it is subjected to tension and compression. Like we're gonna keep on tension and compression, cyclic stress along its axis. If the maximum tensile and compressive loads are with these values, so the maximum stress, this is the maximum compressive and tensile loads. So the F maximum, the maximum force, it is 22,000 Newton, and it is tension. And the negative 10, because it was mentioned respectively, it means that the tensile force, it was mentioned first, and the compressive force comes next, and that's why we do have a negative here. So this is the minimum compressive force as negative 10,000 Newton. Make sense? As you can see, he mentioned here that it is repeated. What does it mean, repeated stress? As we discussed there, that over this slide that in case that would have a repeated stress, its maximum and minimum, they don't have the same value. They do have different values, different signs, yes, but in the meanwhile, they should have different values. They do have different directions. In the meanwhile, they should have different values. But in case that it was mentioned reverse it means that the maximum has the same value of the minimum. For example, you would be given the same example. And one another example that found in the exercise sheet, it was mentioned here reversed. Compression and tensile stress with a force, and you will be given only one value. So this value, is it maximum and minimum? This is the same value for both, but one is going to be tension, the other one will be compression. But here he mentioned repeated, it means that the magnitude of the maximum force, it will be different than the magnitude of the minimum force, and this is what we have. We'd have 22,000 and we'd have 10,000 for the forces. Make sense? It is required to calculate the minimum allowable bar diameter. This bar, it has a diameter D, and it is subjected to a stress subjected to a force. According to chapter 6, what type of the stress that can be generated over this bar? It will be tensile stress or compressive stress is going to be the force divided by the area, 0. If you recall from chapter 6, we have defined this expression as pi over 4d square, which is the diameter, and this was the expression that we introduced for the stresses at the axial stress acting over this bar. So the question is, what should be the minimum possible value for this diameter to ensure no fatigue failure will not occur, or there is no fatigue failure that is going to take place in case? So what should be the minimum value of this diameter? If this diameter is too small, fatigue failure is going to take place. If it is not small, there is no fatigue failure in that case. And the steel has a yield strength, so the yield strength, sigma yield of the steel was given by 240 megapascal, and assume a factor of safety of 2. Factor of safety, mechanical engineer could have an idea about the factor of safety. We are in terms of engineering application in general, whatever mechanical, civil, or in general in terms of engineering application, when we do design to any material, to any system, we should consider a factor of safety. It means that, for example, we shouldn't determine according to this criteria, for example, according to this criteria, this sigma equivalent, as we mentioned, it should be lower than the sigma equivalent, it should be bigger than, or at least it should be equal to the the amplitude stress, which is sigma maximum negative sigma minimum over 2, right? In order to avoid no failure, to avoid the failure, in order to have no failure, this sigma equivalent should be bigger. But for example, if we're going to consider equal, so we are at the critical. So any other factor that we didn't consider probably could lead to some fatigue failure. So we have to consider a factor of safety. We have to avoid even the limit. We have to work below the limit with a certain factor, with a certain value, depend on the factor of safety. So that's why we would like to achieve a factor of safety of 2, and I'm going to let you know how we can involve this factor of safety. So the procedure to solve this problem, remember that the requirement, it is required to find the diameter of the bar, the minimum diameter, how much it is. So the first step is just to calculate the maximum and minimum stresses, which are sigma maximum and sigma minimum. So how we can calculate sigma maximum and sigma minimum? We said that in chapter 6 that the stress, it should be the force divided by pi over 4 the diameter square. The thing that is going to change, that gonna make this stress maximum or minimum, is the force itself, but the diameter, it won't gonna change. So the sigma maximum, we're gonna say it equals the maximum force, which is already given by 22,000 divided by 40 pi over 4 the diameter square. We have no clue how much is the diameter, but we already have the force at 22,000 pi over 4 the diameter square. So this is for the sigma maximum. Do the same for sigma minimum. It's gonna be negative F minimum divided by pi over 4 the diameter square, which is gonna be the negative of 10,000 divided by pi over 4 d square. Make sense? So we got the sigma maximum and minimum, and this is the first step. The second step is just to calculate the amplitude stress and the mean stress. According to the mean stress expression, this is the mean stress, which is sigma mean. It should be the sum of the maximum and minimum over 2. So if we did the calculation or the substitution sigma mean, it's gonna be the sigma maximum plus the sigma minimum over 2 equals, how much is sigma maximum? We already got it by 22,000 plus, it should be divided by pi over 4 d squared. So we could consider this is like a common factor and we can plug it into the denominator. So in the denominator we should have 2 times pi over 4 d squared, because these two denominators, they are common. So we can simply sum the 22,000 plus the negative of 10,000. Make sense? So if we did the calculation, this negative will be multiplied times the positive. This gives 22 negative 10,000. You got my point? Then do the calculations, everything except the diameter, because we have no clue how much is the diameter. We don't have its value yet. So your objective is just to calculate the mean stress, which is going to be 7,639.43. Just do the calculation to all the numbers except just get on the diameter. Then you're going to calculate the amplitude stress, which it should be the sigma maximum negative the sigma minimum. So the difference between the mean and the amplitude is this sign in the middle. So sigma maximum, it is 22,000 negative. We're going to do the same. We're going to consider 2 times pi over 4, the diameter squared, this term which will be common factor in the denominator, negative times negative 10,000. So as you can see, the negative times negative will be switched to positive, and this is going to give the sum of the 22 plus the 10 equals, if we did the calculations, we just going to carry on the diameter in the denominator, do the calculation to the other number, we're going to end up with 20,371.8. So this is for the second step. So the first step, simply just calculate the maximum stress, the minimum stress, plug them here in order to calculate the mean and the amplitude stresses. Then the third step, from the given figure, your objective is just to find the endurance limit or the fatigue limit, which is sigma fatigue. We said that this endurance limit depends on the material type. In case that we do have a material with a fatigue limit like the steel. Steel, it has a fatigue limit. So what is the fatigue limit? Your objective is just to try to draw a line, horizontal line, that is going to intersect with the vertical axis from this horizontal line that indicate the fatigue limit of the material. And just pick the value of the stress next to this line. It is going to be like around 310. And take the unit, which is megapascal. So it means that from the figure for the steel, why steel? Because the material as given it was 1045 steel bar. So it means that from the figure we're gonna get the fatigue limit by 310 megapascal. This is what we got from the figure. Make sense? Then your objective is just to substitute into the fatigue criteria. The fatigue criteria criteria of Soderbergh that we are using, it states that we should first calculate the sigma equivalent. The sigma equivalent, it should equal to the sigma fatigue times 1 negative sigma mean divided by the yield strength, which is already given by 240 square. This is just to calculate the sigma equivalent. But we have to consider the factor of safety. As long as there is a factor of safety, we have to consider, we have to assume that the fatigue limit, it is not 310, it could be less. And the difference between the 310 and the lower value that we choose for the fatigue, this what gives the factor of safety. So the factor of safety to consider, plug it here, you should divide the fatigue limit that you subtract from the table by the factor of safety to avoid any possibility of the fatigue failure due to any other factor that we didn't consider in these calculations, even in the calculation of the forces or the stresses, because we are assuming that the material is subjected to a maximum force is 22 and minimum force of negative 10. But probably there could be some other types and forms of forces which is very negligible but we didn't consider. and probably they would lead to a fatigue failure. So to avoid any other circumstances or unexpected failure of the material, we should consider a factor of safety as already given to us by 2. So your objective first is just to calculate this sigma equivalent, and you should keep in mind it should be bigger than, or at least it should equal to, the sigma amplitude that we calculated. We calculated the sigma amplitude here in terms of the diameter. So this is the condition that we're gonna substitute. So simply sigma fatigue, the fatigue limit, we got it by 310 divided by the factor of safety as given by 2 times 1 negative the mean stress, we got it by 7,639.43. So it's 7,639.43 divided by the diameter square. There should be here divided by the diameter square, so divided by the diameter square. Make sense? So this is just sigma mean. And the yield strength, it was given to us by the yield strength of the material 240 megapascal, which is 240. So this is going to be 240. All of this should be squared as already given here. This in the meanwhile, it should equal to, at least it should equal to the sigma A. So as you can see, that's why he mentioned what should be the minimum allowable diameter. The minimum allowable diameter to be determined, it will be at the critical value at this equal, in case that this is equal sign. But in case that this term is bigger, we're going to end up with a diameter which is going to be bigger than this minimum value. So since he requires the minimum allowable, we plug it equal here. And this sigma amplitude that we calculated by the 20,300, so 37 1.8 divided by the diameter square, which is the amplitude stress. So as you can see, we're going to end up with an expression in only one unknown, which is the diameter, that should be solved. So if we decided to rearrange this equation, we're going to end up with a quadratic form or function of this diameter. We're going to end up with 155, the diameter power 4, negative 2037 1.8 diameter square, negative 1570.46 equals 0. So we're going to end up with a quadratic form. You can use the calculator or the quadratic formula to solve for the diameter. You're going to get two different values for the diameter square. One value that you're going to get as 138.7, and the other value is d square will be negative 7.3. You're going to reject this one. Why? Because the negative is going to give you an imaginary value for the diameter, and the diameter should be real positive value. So it means that this value will be rejected, and then you're going to calculate the diameter from this d. So this is the last step, just to solve for the diameter. This expression solve, you're going to find the diameter equal to the 11.78 millimeter. So this is going to be the diameter of the bar that is needed to avoid, this is the minimum diameter that is needed to avoid the fatigue failure. In case that the diameter, it is lower than this value, with any slight value, whatever it is, there is a high possibility that this material is going to fail because of the fatigue. But in case that the diameter it is bigger, that is fine. We are pretty sure that there is no fatigue failure that is possible, or there is no possibility for the failure of the material because of fatigue. Make sense? Another mechanism of the material failure is the creep. Material could fail because of fracture, because of fatigue. Also, it could fail because of a creep effect. So what is the creep? It is a time-dependent and permanent deformation. As we discussed in chapter 6, what does it mean, a permanent deformation? Or when the material exhibits a permanent deformation, it means that there is a plastic deformation of the material. So the permanent deformation, this is the plastic deformation of the material. And in the meanwhile, it is time dependent of the material when it is subjected to a constant load or stress. So the condition that this load, it should be constant over time. But the deformation, the plastic deformation of the material, it's going to be time dependent. So again, the applied load or the stress, it is constant, not changing in terms of magnitude, neither the direction of the stress or the load, it is constant. But the thing that it changes over time and depending on the time is the deformation, the plastic deformation of the material. This creep effect, just to explain it to you, assume that you do have a beam like this one, and this beam is fixed at two plugs from one side and the other side. Just holding this beam over two levels as shown here. And for some reason you just gonna apply a force over this beam. But this force, as I said, like you just gonna put a load, like you just gonna put a weight. So this weight is gonna give a force, generate a load weight over this beam. And you're just gonna leave it for a while. While it means that you're just gonna leave it for hours. So, but in the beginning, once you put the weight over the beam it will be bended somehow. Even if the load it is not that big to achieve some plastic deformation, assume that it is elastic deformation, and you just put the weight over the beam. So instantaneously, if you just put the weight for 2 minutes, even if for 30 minutes or even for an hour, and then you lift the load, this weight, the beam will restore back again to its original straight position. It means that we're still working in the elastic behavior. But how about if you just gonna leave this weight for a while? This while, as I said, it's gonna be for days, for months. You're just gonna leave it there. So despite that the weight it is not big enough to produce even plastic deformation of the material, once you return back again after months and you try to lift this weight of the beam will not be straightened back again. Even if you spend more time, you probably when you return back, you're gonna find this beam has been broken. So what is the reason? The reason is a fatigue effect. The fatigue effect, despite that the load that is you are applying over the beam, it is constant, it is not changing. You just put the weight and you lift and for months. And when you return back, you're gonna find that either it is plastically deformed, even if you lift the load, or it had been already broken. So what is the reason? Is a creep effect. The load is not changing in terms of magnitude or direction, but the thing that is it changes over time is the deformation. And this deformation, it will change from being elastic to plastic, and even is gonna keep the plastic deformation is gonna keep on it change till probably this beam could completely separate, completely fail or fraction. So the creep is usually undesirable. It is one of the phenomena that exist in metals. It is undesirable phenomena that we try to avoid because it would limit the lifetime of many of the particles of parts or mechanical components. For metals, for example, creep become serious, and we should seriously consider the creep over metal parts in case that they are used at elevated temperature as 0.4. TM stands for the melting temperature of the metal material. In case that we are talking about metals, they are going to be severely affected by the creep effect, especially in case that they are working or are maintained at a temperature level higher than 0.4 of their melting temperature. So what is gonna happen during the creep process? What are the different stages of the creep failure? So as I said, so these are the different phases, and this figure represents the creep strain and the time. So what does it mean, a creep strain? Creep strain, this is the amount of the strain, the further strain that is going to be generated in the material because of the creep effect. As I said, once you put the weight over the beam, the weight will produce some deflection, will produce some strain. This strain mostly, it is small strain known as the instantaneous elastic deformation. It is elastic. We're still in the elastic behavior. And as I said, once you remove the load, if you put the weight and you just lift the weight directly, put it and lift the weight directly, the beam will restore back again to the straight position, indicating that there is still elasticity. We do have elastic deformation in the material. So initially, once we put the load, there will be an instantaneous deformation of the strain. So this is the initial strain. But this strain, this instantaneous deformation or this instantaneous strain, it is not a creep strain. So we put the load, we put the weight over the beam. So there is an instantaneous deformation, elastic deformation due to the applied constant load or stress. Then we're just gonna leave it for a while, 4 hours. So here we have the creep strain and the time. So what does it mean, the creep strain? This is the further, the more strain that is going to generate over the beam because we're gonna keep this load applying for a while. And this applied strain is gonna keep on increasing as the time increases. So as you can see, we're gonna end up with a change in the creep strain, the extra strain that is going to generate because of the creep effect with the time. Initially, we can break down this curve into 3 regions. One is the primary region, the secondary, and the tertiary region. So these are the 3 regions, and let us investigate how these creep strains. The creep strain is going to change through these 3 regions of this creep strain time curve. So in the primary, or known as the transient creep, within this region, we do have a decreasing creep rate. What does it mean decreasing? As you can see, this curve, it is curved down, it goes down, it is curved this way. But if you're gonna compare it to the tertiary region, it goes up, it is open up, but this one is open down. This opening down indicating that we do have a decreasing creep rate. So what does it mean? It means that within this region, the primary region or the transient creep region, the creep strain is going to increase, but it's going to increase with a decreasing rate. So what does it mean this? We do have in general, overall, the strain is going to increase as shown in the curve here. But this strain is going to keep on increasing with a decreasing rate. So what does it mean? It means that after a while, if we're going to follow the same curve, we should have this curve is going to keep on and it will reach a constant rate. Even probably it could follow another decreasing rate. You got my point? Or decreasing strain. So this is what does it mean, a decreasing rate. So there is a difference between the strain and its rate. The strain itself, it is increases, but its rate, it decreases. You got my point? So it increases with a decreasing rate. This is what does it mean. This is the how the strain, the creep strain is going to increase within this region. This is for the primary region, but how about the secondary region? In the secondary region, we do have constant creep rate. So what does it mean? It means that we still have the creep strain is increasing, but with a constant rate. It is almost a straight line. Within the tertiary region, the third region, we do have an increasing creep rate. So in all the 3 regions, the creep strain is increasing. But within the primary region, the creep strain, it increases with a decreasing rate. In the secondary region, or the secondary creep, the creep strain, it increases but with a constant rate. Within the tertiary creep, the creep strain, it increases but with an increasing rate. Make sense? So this is the difference in the rate of the increase of the strain with time within the 3 regions. Another difference is that within the primary or the transient creep, there is an increase in the strain hardening. As we discussed in chapter 7, strain hardening, it means that there is a multiplication of the dislocation. So here is the process how it is worked. That we start with an instantaneous plus elastic deformation. Initially, we apply elastic deformation once we put the load. If we remove the load directly, there is no deformation, and the beam will restore back again to the straight position. But if we're gonna leave this weight for a while, we're gonna move through the primary creep or the transient creep. What's gonna happen in that case? That this elastic deformation will change to be a permanent plastic deformation. And as we discussed in chapter 7, the plastic deformation, it should involve a dislocation motion. It should involve a dislocation motion. So what's going to happen in that case? Remember that mostly in this case, under this creep effect, we're going to leave it for a while and we are working as cold, in the cold condition, at the room temperature. So in this case, we're going to have an effect of the strain hardening. It means that there is a possibility for the dislocations inside the material microstructure to be multiplied, to increase. So we're going to have a continuous increase in the dislocation density inside the material microstructure within this period of time, within the primary region. As the dislocation density increases, this is going to decrease the possibility for the dislocation to move. Why? Because these dislocations, as we discussed in chapter 7, they are going to interact with each other and they're going to impede the motion of one another. This is going to make the achievement or the attainment of the plastic deformation inside the material microstructure. It is kind of difficult, and that's why we're going to have a decreasing rate within the primary region. So why within the primary region the creep strain, it increases but with a decreasing rate? The reason is because of the increase of the strain hardening effect. The strain hardening, it multiplies the number of the dislocation density or dislocation inside the material microstructure and increases the dislocation density. As the dislocation density increases, this gives more resistance to the plastic deformation inside the material microstructure, because these dislocations, they're gonna impede each or one another, and this gives more resistance to the plastic deformation and more resistance to the creep, or the plastic deformation that comes because of the creep, which indicate a creep resistance. So it means that the material still have the ability to resist the creep, but we still have a plastic deformation that is going to generate an increase in this creep strain, but with a decreasing rate. But within the secondary region, we do have a different thing. Competing mechanisms of strain hardening and recovery. Strain hardening, it used to multiply and increase the dislocation. Recovery do the opposite. As we discussed in chapter 7, recovery, it decreases, relieves the stresses inside the material microstructure, relieves the residual stresses and the lattice strain, and in the meanwhile, it decreases slightly the dislocation density inside the material microstructure. So we're going to have two competing mechanisms here. We're going to have a decrease, a decrease competing between the strain hardening. The strain hardening is going to increase the dislocation, but in the meanwhile there is a recovery that is going to decrease the dislocation. So almost we're gonna maintain the dislocation density constant within the secondary region, and this is why we do have a constant increase rate of the strain. So as you can observe that somehow the rate of the strain, the creep strain increase with time depends on what? Depends on the dislocation. As there is new dislocations are going to generate inside the material microstructure, this definitely indicates that we do have a decreasing rate, and is going to affect and decrease the rate of the increase of the creep strain with time. But in case that we do have the same, almost the same dislocation density, so we're going to have a constant increasing rate. Within the tertiary region, we have other things. Grain boundaries separated. This is the material within the tertiary region. You could say that the material gets ready to be fractured to the complete rupture and separation and complete failure at the end. So we start the process by grain boundary separation. The dislocation density is still there, but the creep strain is going to keep on increasing till it will be big enough to separate the grain boundary, break the grain boundary, and the formation of internal crack will start to show up, and cavities and voids will be formed and generated inside the material microstructure at the end. As the time increases, we're going to reach to the complete separation and failure of the material by the rupture. And the time that it corresponds to the complete separation of the material is known as TR, which is the time to rupture or the rupture lifetime of this material due to the creep effect. So these are the different phases and the stages, how the creep is going to propagate and the evolution of the creep with the time till the complete fracture or separation of the material. Make sense? So these two figures represent the relation between the stresses, the temperature, and the creep strain, or the creep behavior of the material. So with the increase in general as shown in this figure, this is what we can understand from this figure as the temperature or even the applied stress, either one or both, is going to increase. This definitely is going to increase the instantaneous strain, which is the strain within the initial strain, the elastic strain, also is going to increase the steady state creep rate, is going to increase the steady state creep rate, will be increasing within this steady state region, which is the secondary creep or the steady state creep within the second region. And then the Curvature lifetime will be decreasing. It means that this material will survive shorter period of time till it will be completely fractured. So as you can see, for example, in case that the temperature for metal, this is generally for metals, in case that the temperature is less than 0.4, the melting temperature of the material, we're gonna have the primary region, this is the instantaneous strain, then we're gonna have the primary, then in the secondary, the steady state creep, it will be maintained, and the tertiary region, which is the third region, to be fractured, we barely can observe any fracture for this material because of the creep, as long as the temperature is less than 0.4, the melting temperature. But in case that the temperature it is higher, or even the stress it is bigger than a certain value, a specific value, in that case the temperature, the material could fail, and we're gonna have the third region. So this is the second region, which takes long time in comparison to the primary region or the tertiary region, the third and the first and the third. The second region, the steady state creep, takes the most long time to take place, and then we're gonna have the tertiary, then the Curvature. But this is gonna be the curve. The Curvature time, as you can see, is going to be declining and decreasing as we are increasing the temperature of the stress. This figure here shows the relation between the applied stress and the Curvature lifetime. As you can see, as we are increasing the stress, the Curvature, for example, if let us choose this material, at this stress level, the temperature, the lifetime will be with this value. If we decreased the stress, it will live longer. It's gonna endure longer under the creep effect. It's gonna take longer time till we achieve failure because of creep. But also, if we're gonna increase, as we increase the temperature at the same stress level, so let us choose, for example, this stress level here, this one, this is stress level, and we are increasing the temperature. Decreasing the temperature. So this temperature, it is less than the temperature of this curve, the green curve. It has a bigger temperature, higher temperature than the blue curve, and move down. So we're gonna get the time. Like if you're gonna compare the time of this point with this point, this curve is gonna Curvature quickly than the blue curve at the same stress level. So as we increase either the stress or the temperature, we are expecting shorter Curvature time for the creep. Make sense? If we decided to calculate, especially within the secondary region or the steady state, as I said, here we do have a declining or a decreasing strain rate. Also, we do have an increasing strain rate over the tertiary region, the third region. But within the second region, the secondary region, or the steady state region, this is the one that takes the most of the time. This is the most dominant region and behavior, and it is steady state. So in many of the cases, when we are studying the creep behavior of the material and investigating whatever we do have a failure due to creep or not, we are focusing more over the steady state region. So if we are interested in investigating or determining the steady state rate, as I mentioned, within the difference, the common between these three regions is that the creep strain is increasing, but its rate, here it decreases, there it is constant, there it is increasing rate. So here the talk is about the strain rate, not the strain itself. So to understand it, the difference between the strain and the strain rate is epsilon, as we discussed in chapter 6, this is the strain itself. But if you divided this epsilon over time, this gives the strain rate. Gives the strain rate, which we're gonna give it the symbol as epsilon dot. So epsilon dot, this indicates the strain rate of this material. So as we said, within the primary region, this strain rate, it should be decreasing with time. It should be, so what does it mean should be decreasing with time? It means that it should be function of time, and this function indicating a declining or decreasing function of time. Within the tertiary region, it should be also function of time, but it should be increasing. But within the secondary or steady state region, it should be function of time, but it is a constant function, gives like a linear relation with the time, or even with the stress. So if we are gonna focus on the steady state strain rate, the strain rate within the steady state creep region, this middle region, the second one, forget about these two regions because they are very negligible in terms of time in comparison to the time that is used for the secondary or steady state creep. So let us focus over this one. So the steady state, so SS stands for the steady state strain rate within the secondary steady state region equals either K1 sigma to the power n or B sigma to the power n. Anyway, either K or B, it is a constant. So this is a material constant that depends on the material type. This exponent, this sigma, this n, it is another exponent that also is a material constant. So as you can see, we do have a bar law between the applied stress. So this sigma, this is the stress that is going to apply. And as we said, as we're gonna keep on increasing the stress, we are expecting a decrease, an increase in the instantaneous, the steady state creep rate will increase, and this is the expression. So as the applied stress is going to increase, the steady state strain rate will increase as well. And this is very clear from this figure. So this figure is different than these two figures. This figure here we are representing the stress versus the rupture lifetime, till it will be fracture because of the creep. But here we are representing the stress versus the steady state. So the horizontal axis here is the steady state rate, steady state strain rate, which is steady state creep rate as r to the power -1. So as you can see, if we just pick the blue curve, for the same stress, for example, for the blue curve at the stress level of 30 megapascal, this is going to be the amount of the steady state strain creep rate. If we're going to keep on increasing, if we increase the stress, the amount of epsilon dot SS will be increased. Make sense? So this is an example about this case. Like if we do have a material sample that is 1015 millimeter long. So this is the original length. Assume that you do have this material that is made of low carbon nickel alloy. Low carbon nickel alloy that has this figure. So this figure, this gives the creep that describe the creep failure of this copper nickel alloy is shown in this figure at these three different temperatures, right? So this is the stress versus the epsilon S dot. This is the steady state creep rate. So if in case that this material, we made a sample of this material with a length of 1015 millimeters, so 1015 millimeter long, is to be exposed to a tensile stress. So this is the applied stress, which is this sigma into this expression. Sigma, the applied stress was given by 70 megapascal. In the meanwhile, he should tell you what is the temperature. As we said, both the stress and the temperature, as we are increasing both, this is going to increase the steady state creep rate within the secondary region, right? So we are expecting, as the temperature increase or the stress increase, we are expecting an increase in the epsilon SS dot. So at the temperature, so this at this stress level, 70 megapascal, at the temperature is already given 427 degrees Celsius, it is required to determine the elongation after 10,000 hours. So how much is the elongation, the time period till we perform the creep effect? It should equal to 10,000 hours. We said that the epsilon can be converted into epsilon rate or strain rate divided by the time. So we can simply say that the steady state strain rate, it equals the steady state strain divided by the time period for this steady state period, which is this period of time. From that point, from this point up to this point, the difference between the time over here is going to be delta t. If you divided the delta epsilon over delta t, this is going to give you the epsilon dot steady state. And this is what is required in this problem. It is required to calculate the amount of the elongation. And in order to determine the elongation in the material sample, we should first determine the epsilon SS, not epsilon dot. But anyway, we're gonna discuss this point. Assume that the total of both instantaneous and primary creep elongations is 1.3 millimeter. Remember that this expression only is valid for the secondary region. For the secondary creep, for the steady-state creep. How about the elongation in the material due to the primary and the instantaneous deformation? We have to consider this as well, because we can calculate the elongation just because of the steady-state creep. How about the elongation because of the instantaneous deformation and the primary creep? This were given both, as mentioned here. Assume that the total of both instantaneous elastic deformation and the primary creep elongations is 1.3. So this delta L0 is going to be 1.3 millimeter. This is the initial elongation that comes because of the instantaneous elastic and the primary creep. And once we calculate the elongation due to the steady state, we're going to add it to end up with the total elongation, and this is what is required in this problem. So it is required how much is delta L total, how much it is. So to solve this problem, the first step is just we can even start from the requirement. What is required here? It is required to calculate delta T, delta L total. So delta L total, the total elongation in this material, it should equal to the elongation. Referring to this, the total elongation up to this point, up to this temperature, it should equal to the elongation due to the elastic strain and the elongation due to the primary creep strain and the elongation due to the secondary steady-state creep strain. So the total elongation, it should equal to, the total elongation will be the sum of the elongation within the due to the instantaneous elastic deformation plus the elongation due to the primary creep plus the elongation due to the steady state. So he gave us into this problem, he gave us the sum of the total both instantaneous and primary creep, these two sum by 1.3 millimeters. So how much is this part to calculate the delta total? So it is required to calculate the total elongation within this specimen after 10,000 hours. How we can determine this? We need to calculate the strain. So to determine the delta L steady state, we should find first the delta S epsilon SS, which is the steady state strain within the steady state creep. This strain, it should equal to the delta L steady state divided by the original length, which is already given 1015 as we discussed. Any strain, whatever it is, it should be according as engineering strain, it should equal to the delta L, which is the elongation in the material specimen, divided by the original length of the material as we discussed in chapter 6. So simply we can determine this steady state length as long as we do have the steady state strain within the secondary region and multiply times the original length, which is already given to us. So the only missing thing to calculate this delta L steady state, we need the steady state strain. So how we can find the steady state strain? The steady state strain, it is related, if we divide it by the time, which is 10,000 hours, we're gonna keep it for 10,000 hours. This should give us the epsilon steady state, the rate, the steady state strain rate within the secondary region. Make sense? So how we can determine, the time was already given to us by 10,000. So the only thing to calculate this epsilon SS, we need the steady state rate within the secondary region that we can get from this figure. So we started from what is required and we investigated what exactly that we have to calculate. So the first thing that we need to determine here from the figure, you're gonna determine the epsilon S dot, how much it is for the given stress and the temperature. So for this applied stress, which is 70 megapascal, the temperature of this material, it is 427. So at 427, it means that we are working over this brown curve, this brown line, and the amount of the stress is 70 megapascal. So your objective is just to identify the 70 megapascal is going to be this line, because this is 60, 70. No, it's going to be like between, because this is 60 and this is 80. So yeah, this dash in the middle is gonna be the 70 megapascal. So next to the 70, your objective is just to move horizontal till you cut with or intersect with this line. Then you're gonna drop down till you're gonna find an approximate value of the steady state creep rate, which is epsilon SS dot from this figure. If you're gonna find it, it's gonna be like around, as you can see, it is like around 7, because if this is like 1 and this is 10, so this is gonna be like around 7, and it's gonna be 7 times the lower power, which is 7 times 10 to the power 7. So it's gonna be 7 times 10 to the power negative 7. As you can see, the unit here, it is hour to the negative 1. So this is what we're gonna get from the figure based on the given sigma and the temperature. Then simply if you plug it here, we can calculate the delta epsilon steady state. So we can calculate the delta epsilon steady state is going to be the multiplication of 7 times 10 to the power negative 7 times the time, which is 10,000. So it's going to be 10,000 as time. If we do the calculations, we're going to end up with 7 times 10 to the power negative 4 hour to the power negative 1. This is going to be, no, there is no hour to, it is dimensionless, because we already cancel with the hour because we multiply times hour. This time it should be in terms of hour. So we're going to end up with 7 times 10 to the power negative 3. I'm sorry, this should be negative 3 because this is power 4, negative 7. So this gives 7 times 10 to the power negative 3. Once we determine this steady state strain, we can plug it here to calculate the delta L. So from this expression, delta L steady state simply is going to be the delta epsilon steady state, which is 7 times 10 to the power negative 3 times the original length, which 1015. If we do the calculation, we're going to end up with delta L steady state as 7.105 millimeter. Why millimeter? Because the length is already millimeter. So simply if you added this 7 to the 1.3, we can simply calculate the total length of or elongation of the sample as 8.405 millimeter. So this is the total elongation due to the creep effect of this material sample. Make sense? Okay, so that's it for this chapter. In chapter 8, the objective was, as we mentioned, just to give you a hint or an overview about the most common types of the material failure as fracture, fatigue, and creep, and to understand the difference between them and at which situation or cases or application of the material that we would expect a failure due to fracture or fatigue or creep, right? So that's it for this part, and thank you so much for watching, and see you in another video.